Okay, are there questions about the exercise?
So I'm currently still stuck at B. I'm not sure about the others. It's 50 minutes was rather short, I'd say.
Okay, I can give you more. I can give you another 50 minutes.
Yeah, I've no idea about how far the others are though.
Are there other people stuck somewhere? What I could do maybe is show you the answer to A.
I mean, that's perfectly fine by me.
Yeah, but you're 1 out of 30.
I also agree.
You still don't have a majority.
Yeah.
I would like that as well.
To Vlad said something.
Yeah, I also said that I agree with you giving us the answers for the A.
Is it possible for me to send this exercise in the chat to you? Or is it possible to send? I've never tried that with Google Meet. Does anybody know if that's possible?
I don't know if it's possible, Johannes, but if you email it, and I'll put it very quickly on Canvas.
Okay, so I will first email it to Dirk so he can put the exercise on Canvas, and then I can switch screen to an answer. I can't show both at the same time, I think. So let me try and do that.
It should be possible to add a document. I don't know how exactly, but if you click on meeting details in the left lower corner, you can see bijlagen. But I don't know how to add them.
Even kijken, misbruik melden en probleem melden. Instellingen, is het in instellingen?
In the bottom left corner, it says meeting details of vergaderdetails.
Yes.
If you click there, there is an seems to be an option to add an.
Oh, bijlagen hier.
To add something,
I
but
don't know about the option.
You know what? I think the email is safer. Then I know what I'm doing. Here I have no clue. So sorry.
Yeah.
Oké, Dirk, ik heb hem naar je gestuurd.
Okay, I've added them to Canvas, so you should be able to see the document there.
Okay, so the exercise has been posted, and if everything is okay, you are able to see the answer on the screen now. I have written down the answer for E field 1, E1, and you can see that it's proportional, that it's equal to the square root of the reflectivity times a half times e to the power I square bracket k2 times L1 minus omega t close bracket. Is there a question about this answer?
Yes, for the last term, wasn't that supposed to be 2 times the square root of r?
Why would you come to 2 times the square root of r?
Well, don't we have 2 times that integral from integral of s of k times e to the power of k delta z?
I'm not quite sure if I follow. My argument is as follows. The reflectivity of the mirror is 0.001. R is 0.001, and this is valid for the intensity. So if I send an intensity and then look at what is the power then of the reflected intensity, it is 1% of the incident power. But we're calculating E fields. So what does this mean for the E field? By how much is the E field reduced with the reflectivity R?
Oh, and one more question. Wasn't that supposed to be over 2? Because E1 and E2 are E over the square root of 2.
Yes, the E is the square root over 2. E is that is after the first pass through the beam splitter. But you pass through the beam splitter twice.
Oh, okay.
So then going through the beam splitter twice gives you 1 over square root of 2 multiplied by 1 over square root of 2 is a half. And that is the half that you see in the expression for E1. The important thing that I would like you to understand in this exercise is that for the E field, the E field amplitude is proportional to the square root of the reflectivity for intensity. Just as light at the beam splitter, if you look at the intensity, it splits it into half. But that means for the E field, that the E field becomes smaller by a factor of square root of 2. I think these are the two key points in deriving the E field 1 and E field 2. And then to calculate the intensity, we have to calculate the detected E field times its complex conjugate, which is the product that I've written out there. And with your expression of E1 and E2, you should be able to calculate now the intensity and also the interference term. So how many of you were able to get to this answer?
I got something close, but not this one.
Okay. People got completely stuck.
So I got a similar expression, but not entirely correct.
You understand what went wrong?
Yeah, I didn't add the reflectivity with the right methods.
You took the R directly to the square root.
Yeah.
Okay. I would like to look in a little more detail at the answer. So if you look at the answer, we see that it is 0.01 divided by 4 times the E field squared. That is the E field that is entering the interferometer. So this is basically the intensity that can be attributed to the sample mirror with the low reflectivity. If you look at the second term, it's 1/4 of the E field squared, 1/4 of the intensity. So this is, simple to understand. We have the intensity hitting the beam splitter. Half of that intensity goes to the reference arm. It's reflected with a mirror that has a reflectivity of 1. So half of the intensity travels back to the beam splitter. There it splits again into 2 equal parts. So half of that goes back to the laser and the other half goes to the detector. So we end up with 1/4 of the incident intensity. Now we can look at the interference term. And we see that it is equal to, what is it? 0.1 divided by 2. Is that correct? Yeah. So that is a.
Please explain again why it's divided by 2 and not by 4.
Oh, it's because if you look at the expression for e to the power ik2 L1 minus 2 L2 plus e to the power.
You 2 times the cosinus. I don't remember the formula exactly. That's why I'm asking.
Yes, so that is actually equal to 2 times cosine.
Okay, thank you.
So that's where you might be missing a factor of 2. The important thing here is that if we look at the amplitude of the interference, it is 0.05. I'm looking for a pen. So the amplitude of the interference is 0.05 times E squared. And if that's for cosine is 1 or cosine is minus 1. If you look at the constant background, so just the reference per sample arm term, let's forget about sample arm term. It's really small. It's a 1/4%. But the intensity from the reference arm is a 1/4 of the incident field, so that is 0.25 times E squared. If I take the ratio of the interference over the background, I get 0.05 divided by 0.25, that is equal to 1/5, or in other words, 20%. So what I see is that my interference, the oscillations due to the interference, are actually 20% of my constant background signal. And I think that should surprise you in a way, because the reflectivity of the mirror was only 1%. So you see that the interference that I see is much larger than what you would expect just looking at the reflectivity of the sample arm. And again, this is a manifestation of the amplification of your signal by mixing a very weak sample arm signal with a strong reference arm signal. Okay. I will want to let you finish exercise the B and C, and then we'll continue with the lectures. So maybe I should give you a break now, and well, break until 4:30. So I continue at 4:30.